This is problem 7-153 out of your book. We have steam going into an adiabatic nozzle. We're told at state 1, the steam is 2 megapascals, 350 degrees C, and it enters the nozzle at 55 meters per second. And at state 2, we're told we have the pressure is 0.8 megapascals, and the velocity is 390 meters per second. And we're told that the area of the inlet to the nozzle is 7.5 centimeters squared. And what we want to find out is A, what is the temperature at the exit of the nozzle, and B, what is the rate of entropy generation. Let's start with part A. So first we're going to find what is the temperature at the exit, or T2. Okay, so I'm going to start with an energy balance. Okay, there's my energy balance. Now I'm going to simplify it based on what I know about my system and some assumptions I'm making. So I'm going to eliminate my ddt term based on assuming steady state, steady flow through the nozzle. We're told it's an adiabatic nozzle, so my Q dot is 0. There's no work done on or by the nozzle, so that guy goes away too. And then I'm going to neglect any changes in potential energy of the stream coming in and out. Now, note that I've already simplified this energy equation a little bit, because remember, this whole term on the right is m dot in, or m dot at 1 times theta at 1 minus m dot 2 theta at 2. So I've already expanded theta and equated m dot at 1 and m dot at 2 just being m dot, because we have single stream in and out. Okay, so now I use, I simplify what's left of my energy equation, and I can just divide out m dot, since that's just a coefficient to that term. And what I'm left with is H2 equals H1 plus 1/2 V1 squared minus 1/2 V2 squared. Now I can just substitute in the values that I know. I can get H1 from my superheated table, so from table A6, and again I found this, as we always do, I know that this is superheated because I've gone to my saturated water table and I see that my at 2 megapascals and my inlet pressure, my temperature of 350 degrees C is greater than my saturation temperature. So now I have superheated steam going in, and I find H1 equals 3,137.7 kilojoules per kilogram. All right, now I know everything else I need to know, so I can go ahead and solve for H2. So that's going to be, now again, be careful, as we always say, be careful with those units. It's very easy to mix them up when you start combining things like specific enthalpy and kinetic energy, because we tend to use what's right within the table, but we have to be very careful with our units. So I'm writing this as joules per kilogram. That's the specific enthalpy, but in joules per kilogram. And then plus 1/2, or 55 meters per second squared in, minus 1/2, 390 meters per second out. And you can check for yourself and verify that all of these units match. All right, so H2 at my outlet is 3.0632 e to the 6 joules per kilogram, or 3,063.2 kilojoules per kilogram. All right, so now I know two properties at my outlet, at the outlet of my nozzle. So I'm going to go, so at 2, I know P2 is 0.8 megapascals, and H2 is 3063.2. Rewrite that a little bit. Oh, those units don't want to go in there, so we'll just put them down below. Kilojoules per kilogram. Okay, so now I see, same way I always do, I can look at my saturated table, and at 0.8 megapascals, I would see that my H2 is greater than my saturated vapor. So I know I'm superheated. From table A6, I can find T2. So when I do that, I find my values. I find that H at T equals 300 degrees C equals 3056.9 kilojoules per kilogram, and H at 350 degrees C equals 3162.2 kilojoules per kilogram. Now I see that my H2 is in between these two values, so I need to interpolate to find T2. All right, so I'm going to go ahead and interpolate here. 350 minus 300 degrees C over 3162.2 minus 56. Let me just erase that. 3056.9 kilojoules per kilogram equals T2, what I'm looking for, minus 300 degrees C over my H2, 3063.2 minus 3056.9 kilojoules per kilogram. And when I solve, excuse me, I find that T2 equals 303 degrees C. I'll write that a little neater. Okay, once again, T2 is 303 degrees C. All right, now on to part 2, where we want to, or part B, where we want to find what is the rate of entropy generation. All right, to do this, we're going to start with an entropy balance. So I'm going to write out my entropy balance, and this is a balance on my control volume, which is my nozzle. So m dot S, rewrite that a little bit. So m dot times S in minus S out plus Q dot over TB plus, plus the rate of entropy generation. So remember, in our entropy balance, this is the change of the entropy in our control volume with time. This is the rate at which entropy is entering and leaving the system with mass transfer. This is entropy transfer with heat transfer, and this is entropy generation due to irreversibilities. So I can simplify this a little bit. I'm going to assume steady state, steady flow, so my DDT term goes away. It's an adiabatic nozzle, so this guy goes away. It's Q over TB. And what I'm left with is rate of entropy generation, which is what I'm looking for, is m dot S2 minus S1. All right, so now I'm going to start. I have to find each of these things. Let's start with my m dot. I'm going to find m dot using what I know about the entrance condition. So m dot is going to be equal to my velocity at 1 times my area at the inlet. Write that a little neater here. Area of the inlet over the specific volume at 1. So that's going to be 55 meters per second times 7.5 times e to the minus 4 meters squared. I've just converted the 7.5 centimeters squared to meters squared. And then I can go to my table, my steam table, as I've done before, and I can find the specific volume at my initial condition, which I find to be 0.1386 meters cubed per kilogram. And so my mass flow rate is found to be 0.298 kilograms per second. All right, so now what I need to find are my S2, my specific entropy at the outlet, and S1, my specific entropy at the inlet. So let's do that now. So I'm going to go to my tables. So let's start with S1. I find S1 to be 6.9583 kilojoules per kilogram Kelvin from table A6. Again, that's looking at 650 degrees C, 350 degrees C and 2 megapascals. And then to find S2, I need to interpolate to find S2 at 303 degrees C and 0.8 megapascals. So I'm going to go ahead and write out that interpolation. Okay, so once I interpolate, I find that S2 equals 7.2451 kilojoules per kilogram Kelvin. Okay, so now I have everything I need to calculate my S-gen. So I'm going to calculate, go ahead and plug into my S-gen formula, 0.298 kilograms per second times S2, 7.2451 minus S1, 6.95, 9583 kilojoules per kilogram Kelvin. And so then when I calculate my S-gen, I find my rate of entropy generation is 0.0854 kilowatts per Kelvin.